Okay, so for day 4 here, we're going to stay in triangles until Christmas. And so what we're going to be focusing on today are special segments you can draw inside a triangle, what you call them and what they do. There is going to be a lot of vocabulary in this lesson and a lot of properties of those things that you're going to have to memorize. You're going to have studying to do. This is not something you're going to learn and remember in one day. It's not going to happen. So make sure you do that. And so what we're going to start off is we're going to do these bottom 2 first on this chart. And we're going to start with a triangle, and we're going to draw a perpendicular bisector in it. Because that's a special kind of segment you can draw. Now, tell me, what makes a perpendicular bisector be a perpendicular bisector? It's perpendicular, which means it makes a right angle. So this line better make a right angle with the side of the triangle. So it's perpendicular to side. But what else? It's not just a perpendicular. No, it's not perpendicular to the other side. Does that look perpendicular?
It's a bisector.
No, to the...
It's just perpendicular. Now, could it extend beyond? Yeah, it's perpendicular all there, where it intersects. Okay? But what else is true about a perpendicular bisector? It bisects a side. What does a segment bisector imply? No. A segment bisector implies an intersection at a midpoint. So that means this perpendicular bisector goes through a midpoint. But what does the midpoint imply? Collinear segments, and they're congruent. Oh yeah, we are having an implied statement quiz coming up in a week from Monday, and yeah, y'all still need to know those old ones. They keep coming up. Okay? So this orange segment is a perpendicular bisector of this side of the triangle. But how many sides are there to a triangle?
3.
So how many perpendicular bisectors could I draw?
3.
3. And so let's pick a side. Do you want to go left or right?
Left.
I heard left. So let's go to the left. So I need to draw a perpendicular bisector here. What should I try and find first? The midpoint. So just kind of eyeball it. And go, it looks close enough to the midpoint. How do I make sure it's the midpoint?
How do you put the...
I say it's congruent on both sides.
Yeah.
Now it's the midpoint, because I said so. I said it was a midpoint, and it was good. But wait, this is supposed to be a perpendicular bisector, not just a midpoint. How do I turn this into a perpendicular bisector? I need to put something that's perpendicular. So, okay, you have to just eyeball it again. You don't have a compass or a protractor with you. Just kind of eyeball that. Looks kind of perpendicular-ish to me.
Yep, indeed.
Close enough for government work. It's harder than it looks, huh?
Yeah.
You just hit my elbow.
I've been doing this for 30 years, and I still screw it up all the time. That's why you don't trust the picture, you trust the marks. Okay? But wait, there's a third side. We have to find the perpendicular bisector on this third side. So I'm going to eyeball. What do I need to find first? A midpoint. Yeah, maybe right about there, you think?
Yeah.
Sure. And let's make sure it's a bisector by showing that these two sides are indeed congruent. And then I need to be perpendicular to it. So make a right angle and just kind of go through like that.
I see the circumcision.
3 perpendicular bisectors.
It's the thing that makes it...
And you notice what's special about these 3 perpendicular bisectors?
Cross at the same.
They all cross at the same spot. And that's weird in math.
Mine made a triangle. Oh, sorry.
That's because you didn't draw it accurately. If you drew it accurately, they are going to all intersect at the same point. And that's unusual in math. Two things can intersect easily at a point. Getting a third thing to cross at that same spot is trickier. But for some reason, all these perpendicular bisectors will always concur. That means they will occur at the same place. And this point of concurrency gets a fancy math name. Anybody want to guess what the fancy math name is?
Orthocenter.
It's going to be the circumcenter.
Centraloid.
So the circumcenter is the name for this fancy point of concurrency where all the perpendicular bisectors meet. Its name means something. What do you think circumcenter could possibly be talking about? The center of something. Does that look like the center of the triangle to you?
No, man.
No. So it's the center of something else. What's at the center of? What does circum make you think of? Circumference. Like circumference or a circle. It's the center, okay, it's the center of what's called the circumcircle. Because circum means to go around, like to circumnavigate the globe, you go around the world, okay? And so the circumcircle is a circle that goes around the triangle and touches all three corners.
Okay.
I thought we were only doing triangles.
Oh, but it turns out that triangles are related to circles.
That's actually pretty cool.
So this circumcenter is the center of this circumcircle. So the circumcenter is the center of the circumcircle, which is the center of the circle outside the triangle.
That's a lot of C's.
Yep. Center of circle outside triangle. I know my handwriting's garbage.
Wait.
So here's that circumcenter. Here is the circumcircle going around it. So for some reason, perpendicular bisectors come together to make it where you can draw this circle. You could prove this 2,400 years ago, and we're all just like, what? But wait, there's more. Okay? But before we get to the more, let's see if you can remember what perpendicular bisectors are. So in this triangle now, see how there's all these segments drawn?
Yeah.
Only 3 of them are perpendicular bisectors. Color them. Color the 3 that are perpendicular bisectors in this picture. What do you look for? They should go through the midpoint of a side and be perpendicular. So it should go through the midpoint of a side and be perpendicular.
And then they got 3 angle bisectors.
Nope, actually you don't. That's what you get for assuming.
I always assume.
So these are segment bisectors because I'm bisecting a side and a side is a segment. So I'm going to go ahead and mark that they're bisectors so I don't forget that, oh yes, these perpendicular bisectors did indeed bisect the side. But wait, hold on a minute. The center of a circle, what's the distance from the center to the edge called?
Radius.
Yeah, y'all learned that, right?
Yeah.
Is the radius going to be the same no matter where you are in the circle?
Yes.
Okay, get a different color if you're using colors.
Oh my God.
I want you to go from the center of the circle out to vertex B. Is that a radius?
Yeah.
Yes, because it goes from my circumcenter out to the edge of that circle. What about from the circumcenter to vertex A?
Yeah.
That's also a radius.
Oh my gosh.
What's another radius you see here?
The C.
Circumcenter out to point C. But what did you tell me is true about all radii?
They're all in the middle.
They are always congruent. So I'm going to put 4 marks through these.
Oh my gosh.
You put on the wrong one.
Oh, you're right, I did. I should have put it on here. You're right, you caught my mistake. Get candy.
What a lucky boy.
Good job. That should not have gone in the perpendicular bisector. It had to go through the radius, and I oofed that. That's what I need y'all for. Okay? So let's see. So basically, all radii are congruent in a circle. Is that true? radii, radii. All radii are congruent, so the circumcenter, that only has one C, circumcenter is equidistant from the vertices. Vertices are the corners of the triangle. I taught you that word at the beginning of the unit. Once I teach it to you, I'm good to use it any time. Okay? And so let's double check that. The circumcircle goes through the vertices. The circumcenter is the center of that circle. So all these distances have to be equal. Now, are all the perpendicular bisectors equal? Do all those perpendicular bisectors look equal to you? No.
They do not.
So it's interesting. The perpendicular bisectors meet and make these radii equal. Okay, it makes a different set of lines become congruent, which is mind-blowing, but that kind of stuff happens in math all the time, where one set of things happening makes another set of things true. And then we say, well, that was so much fun, let's bisect something else. What else can we bisect in a triangle?
Angle bisect.
Angles! So let's go bisect some angles. What do you think an angle bisector bisects? So it's a segment that bisects angles in a triangle. Well, what do angle bisectors do? What do they imply? Oh, y'all need to study your implied statements. Two congruent, oh look, here are two congruent adjacent angles. So what must this red dude be? It's an angle bisector. Oh,
God, are you serious right now?
crazy. But, my friends, how many angles are in a triangle? So how many angles could I bisect? 3. So let's bisect the other ones. So I'm going to come down to this angle, and this is where you just have to try and use your well-calibrated eyeballs and guess. What looks to be about halfway down that angle? That looks like it's cutting it into about even pieces. And so then I'm just going to draw that line out. And I'm going to say that this angle is congruent to that angle. Notice I put a different set of angle marks in it. Because this could be a scalene triangle. And if all those angles were different, then these bisecting things will be different. And so I've got 2 angle bisectors. Could we go for 3?
Oh, surely could.
Surely could. So go ahead and go for a 3rd angle bisector. So I'm going to just eyeball it. See, that looks like that's about down the middle, maybe.
Yeah.
Pretty close?
Yep. Couldn't we just take it from the middle and then draw it to the line?
Oh, well, that would imply that all the angle bisectors met at a point of concurrency.
Oh no, like whenever you drew your 2 lines.
Yeah, so you're saying this one should go through the same spot the other 2 did?
Yeah.
Oh, guess what?
What?
You're right.
Let's go.
It's not straight. That means vertical.
Now make sure you mark it. To prove that it's an angle bisector, those angles should be congruent. Will you go sit over there at that table, please? I'm tired of interrupting that conversation. So I've got my three angle bisectors, and oh, conveniently, they all meet at a point of concurrency. We should give it a fancy math name. What should we call the point of concurrency for the angle bisectors?
Insector.
The incenter. Now, we probably called it an incenter for a reason, huh?
In the center.
Because it's in the center of something. What do you think it's in the center of?
The circle. A circle.
It's the center of the in circle.
Wait,
The circle inside.
That's a circle inside the triangle.
what circle are you drawing? Oh, I think I might get it.
Is it the circle inside the circle?
It's a circle inside the triangle.
So like, it's miniature,
So,
right?
if I take this incenter here, it should be the center of some circle. And so I'm going to draw that circle. It's going to be inside the triangle. Well, I could draw lots of circles inside, couldn't I? This is the circle that touches all three sides but never goes outside. So it's going to look something like this.
What was that?
I'm not really sure, and I'm not sure I want to know. So this is your in circle.
Very interesting.
Okay. Now that I've drawn my in circle, go into this picture now and color the three angle bisectors that created that in center of the circle.
Okay.
So color in now, go think again. How did I find angle bisectors? What do angle bisectors do? Okay, so find one of the angles, and oh yeah, that looks bisected, so this must be one of the angle bisectors. And this looks bisected, so this must be one of the angle bisectors. And this looks bisected, so that must be one of the angle bisectors. Are all my angle bisectors the same length? No. But for some goofy reason, they all come together at that one point, and we call it the incenter, and it's strangely the exact center of this circle that you can draw inside the triangle.
Oh.
These are massively useful in building engines, machines, and anything that's got wheels or gears in it.
How do you find the center of the triangle?
Well, it depends on what you define as the center of the triangle. Are you talking about the center of a circle inside it? Are you talking about its center of mass? What does the center of a triangle mean?
The center of the
Is it equidistant from the vertices, or equidistant from the sides, or is it the balance
equal
point?
distance from the birds.
Well, no, that would be this one then. This is equidistant from the vertices. But guess what this one is?
From the angle find the center of the triangle.
This one, remember, this is a circle, right? If I draw a perpendicular from the center out to the edge of the triangle, it's right where the circle meets, and it's perpendicular. And if I go from the incenter out to this part of the circle, where it touches the triangle, it'll be perpendicular there as well. And if I go from the center to where this edge touches the circle, that will be perpendicular. All three of those segments I can draw, these are not the angle bisectors. These are radii of this circle. See how it goes from the center out to the edge, center out to the edge, and center out to the edge? What's that part called when it goes from the center out to the edge of a circle? And what's always true about radii? They're always congruent. So this incenter is equidistant, the same distance to all three sides. So the incenter is equidistant from the sides this one's gonna have fine print. If that distance is always gonna be the shortest perpendicular distance to the side, okay? Because if I start moving off of there, it's not the shortest distance anymore, and we always call distance the shortest one. And so here's a funny fact then. If I bisect the sides, I'll be equidistant from the corners. If I bisect the vertices, I'll be equidistant from the sides. So it's like opposite land. Whichever one you bisect, that point of concurrency will be equidistant from the other thing. So here I perpendicular bisected the sides, I'm equidistant from the corners. Here I bisected the corners, I'm perpendicular and equidistant from the sides. Why does that happen? Because math is cool! That's why. And you wouldn't expect that! You've been doing triangles all this time in your life. You would never expect this randomness to happen where suddenly circles are involved. But it is! And what's crazier is, oh look, what shape is this in this bottom corner?
Triangle.
What kind of triangle?
Right triangle.
So if I wanted to, if I move this length and this length, could I find that distance out to the corner?
Yes.
Yeah, because I could use the Pythagorean theorem. So suddenly we're pulling in all this different junk from all the other math you've learned randomly from bisecting junk in a triangle. And as mathematicians, this happens to us all the time. We just discover that things are randomly related. And it's so cool. How are you going to remember all this garbage?
Study.
Yeah, but it helps if you have a mnemonic device, right?
What?
Phone.
A remembering device.
Oh.
Turn the page over.
Looks like we got some of those.
How will I remember all this?
A lot of peanut butter cups may contain apple butter.
And so we've got this statement. And this will help you remember everything on this side, but we're going to focus just on the two we did today. An odd peanut butter cup may contain apple butter instead. So you go to eat a peanut butter cup, and every now and then, randomly, you might get apple butter, which, by the way, is extremely tasty. Okay, it's like apple jam, almost, but creamier. It's really good.
It happens.
It's really good. And so what you're going to do is this phrase helps you remember what goes together, because each pair is a reminder of what goes together. So for example, we learned about perpendicular bisectors today. Perpendicular bisector. That starts with P and B. Guess what it goes with?
Peanut butter.
Peanut butter. And so the perpendicular bisectors that start with P and B, just like peanut butter, are going to have a concurrency point at something that starts with C. What was it? What was our point of concurrency for my perpendicular bisector? Circumcenter. What was the other special segment we learned about? Angle bisector. What do you think angle bisector will go with?
Probably apple butter.
Probably apple butter. So angle bisector will be going with something that has an I like instead.
In circle.
And that's your in circle. In center.
Oh, yeah.
The in center is the center of the in circle. And I know you want to know what the other ones are, but too bad, I'm not telling you. You have to wait till next class. Ha ha ha.
Are you serious?
I know, you're so disappointed.
Wait.
Instead, let's see what kind of things we can do and find out using our angle bisectors and our perpendicular bisectors. So,
No time for break.
you won't have plenty of time for the quiz.
Quiz. Oh yeah. We do this and the quiz and then we have to work. That's
I thought we skipped the quiz, and we all did one hundred.
So follow along, because this is how I want you to think as you're doing your homework problems. It says, in the diagram, the perpendicular bisectors, which are shown with dashed segments, find them. Which ones are the perpendicular bisectors? Saying those ones is not real helpful to me.
What's with that?
The one that go to this center point here and are perpendicular and appear to bisect the outside, and they're dashed. So here is a perpendicular bisector. I'm going to mark that it's bisecting, and I marked that it's perpendicular. What's another dashed segment in here? D is a point, not a segment. DG. So it's a perpendicular bisector as well. So mark the perpendicular and mark the bisecting. What's the third dashed one? G to F, which is teeny tiny. But it's still perpendicular, and it still bisects this third side. So it's bisecting AC. Okay? So, 3 sides, 3 perpendicular bisectors, are we good? Okay, and they made it point G, which is the circumcenter. So let's find our circumcenter. There it is, it's point G. What's special about our circumcenter?
It's low. Really low.
It's the center of
A circle.
a circle. Which circle?
Outside.
The circumcircle, which is the circle outside. And so I'm just going to sketch that circle outside. And it's not going to be really pretty. It's supposed to touch all 3 corners, if you do it right.
I messed up.
I'm not an artist.
I'm not either. That's why I just say it goes through them and I call it good. Okay? Okay, it gets the point across. Okay? Now, what's special about that circumcenter with its circle? All the radii should be congruent. Which 3 radii do we care about?
DG.
From G, is DG a radius of that circle?
No.
No.
Necessarily.
How about one that goes from the circle to the center? So AG is a radius. What's another radius of that circle? BG. BGs. You can tell by the way I do smell. And what's the last one? Which one? CG. Thank you. Oh, but what's true about every radius in the picture? They're all congruent, so mark them as all being congruent. Well, now we can figure out everything it asks for.
Is this easy?
It's on the camera.
Is this easy?
Okay, so I need to find AG. How big is AG?
As big as it is.
AG would be.
Oh, it doesn't have a number here, but oh look, it's congruent to something. It's congruent to this guy and congruent to this guy. So how big is AG going to be? It's going to be 25.
Yeah.
How big is BG going to be?
It's gonna be 25.
It's another one of those radii, so it will also be 25. So you have to really know how all these relationships work. Okay? What about CE?
15.
But it didn't say 15. How did you know it was 15?
Angle bicycle.
Well, because it's the midpoint has 2 congruent segments, so 15 is gonna be.
Yeah, this part's congruent to this part, so it had to be 15. Nice. What about AC?
Probably like 48 or something.
Or something? Well, it's either 48 or it's or something. How will you figure it out?
Yeah.
Talk to me. Yes?
AF,
Uh-huh.
24,
Uh-huh.
and F is like the midpoint.
Uh-huh.
So F plus C is 24.
So this is also 24. And so the whole thing is 48.
Or something.
Or something.
Don't, please.
Right? Ooh, something different. An angle. The measure of angle ADG. Can you find it?
Yeah.
Yeah, it's this little guy right here.
I know it.
How am I going to figure out how big it is? I want everyone to be thinking, not just waiting for these guys to answer.
Oh.
Everyone be thinking,
Oh, I can't.
how am I going to figure out how big this angle is right here? Well, it's a linear pair and it's perpendicular, so it should be a
90
90-degree angle. Yes?
These are issue.
Yeah.
Thank you.
So here, it tells you if BG is 2x minus 15, then how big is x? Well, how big is BG? It was 25. So is that something I could solve?
Yeah.
Yeah, okay, so we're not gonna, because you could. Then it says if DG equals 15, this guy right here equals 15. It wants to know how big is AD. AD is from A to D. How am I going to figure that guy out?
The square with the thing.
Well, I've got a right angle here, so it's a right triangle, but I only know one side. Or do I?
Yes.
Oh wait, how big is A to G?
25.
It's 25. So could I find that third side then? Yeah.
Indeed.
Is it the hypotenuse of this right triangle or one of the legs? It's one of the legs, so I could do x squared plus 15 squared equals 25 squared to find that missing piece of the side.
Yeah.
Ooh, bringing back some of the algebra and pre-algebra stuff.
Very hero.
Okay. So this is all stuff with perpendicular bisectors. Show.
Wait, we didn't finish.
Oh, I didn't solve them. Y'all know how to solve algebra. I don't need to solve that for you. Okay. No, I'll do that.
Mark.
Now number 2. Point PT is the end center. Okay, mark T. There it is. It's the end center. If T is the end center, what point of concurrency is it? What made it be the end center? What things come together to make the end center? The angle bisector. Yes, you could write the words, but I get lazy. Okay? So it's a point of concurrency of the angle bisectors. So this angle is bisected right here, and this angle is bisected right there, and that angle is bisected by all those pretty little angle bisectors. But then it wants to know how long ST is. How am I going to figure out how long ST is? Well, think about what information they've given me. What is my special point again?
T.
T. It's an in-center. What do in-centers do?
Circle inside.
They're the center of a circle inside.
Oh, indeed.
And that circle inside has radii that go out to the edge of the circle where it touches the triangle. And what's going to be true about all those radii? All the radii are congruent. And WT is 15. So how big will ST be? See how that's going to work?
I am not done.
Okay. Turn it over. we have one more special segment to learn about. We've learned about perpendicular bisectors. We've learned about angle bisectors. Now we have one more, and it's totally different. So, for this one, you get to draw a pretty picture. Graph ORS with these three vertices. So you're going to draw the whole triangle, not just the corners. I'm giving you 20 seconds. Go.
Oh, wait,
Yeah. Pretty serious right now. Yeah.
If you complain less, you go faster.
Could be true.
Oh, I'm smart.
And so you have a pretty triangle now.
No.
And what I need y'all to do is we're going to find a couple of the midpoints of these sides. Because we've been bisecting stuff. So let's find midpoints. So what would be the midpoint of the bottom one? Yeah, that's the easy one. What about from O to R? How will I find its midpoint? Do you remember?
Slope, right?
No, we don't need the slope.
Just like do the way.
We go halfway across the side and halfway up and down. Remember doing that with our T-chart in Unit 1? So how far is it from O over to R? How far sideways do you go?
6.
You go from 0 to 6. So to get to the midpoint, it would only be half of that. So I'd be over 3. How far up and down is it from from O to R?
8.
It's 8. So the midpoint will be halfway up, which is 4. There's your midpoint.
No, what triangle has a midpoint?
Wait, you can just like divide it by 2.
Okay. And so from R to S, how far sideways do you go from R to S? From R to S, how far is it from 6 to 10? It's 4. How much is half of that?
2.
2. So 2 over from 6 would be at 8.
Yeah.
Now I'm going from 0 up to 8 again, so how far up should it be? Up 4. And that's going to be point W. And this bottom one, we'll call it P, because they didn't tell us what to call it. Now, what I want you to do is connect the dots. Connect TW. Okay? Now you have to think back to the dark ages of algebra. Shh. And look at segment OS, this bottom side of the triangle. What's its slope?
0.
How do you know?
It don't grow. Horizontal.
It's horizontal. And horizontals have 0 slopes. So this one's horizontal. But this piece that connected the midpoints is horizontal. So what's its slope? They have the same slope. Interesting. What do things that have the same slope? What's that called when two things have the same slope? They're parallel. What about if I go from T to P?
Oh, we're making a triangle.
Shh. What does this slope equal? What's the slope of this guy?
Negative 2.
It's down 4 over 2, which would, negative 4 halves simplifies to negative 2. What's the slope of RS?
Oh.
Down 2 over 1, down 2 over 1.
That's probably
It's also negative 2.
They're parallel.
Whoa, they're parallel.
Oh my God.
What do you think's going to happen with PW?
Same.
You think it's going to be parallel to OR?
Yeah.
Guess what? It is.
Oh, we're smart.
Okay? So this special segment that we drew that connects the mid-segments, so this purple guy, this orange guy, and this pink guy, they all connect mid-points of the sides. Guess Guess what a segment is called when it connects midpoints?
What segment?
It's called a mid-segment.
Yeah.
Because it's a segment that connects midpoints. And a mid-segment, you guys just discovered, is always going to be parallel to the third side of the triangle. Because it's connecting two of the sides at their midpoints, but it'll always be parallel to that third side. This one connects two midpoints, it's parallel to the third. Orange guy connects midpoints, it's parallel to the third. Pretty cool, right? But wait, there's more. How long is OS?
10. 10 metric units.
How long is TW?
Like
6.
5.
Which is it, 5 or 6?
5.
You notice something special?
Half.
It's half the length of the third side.
Oh my god.
Guess how long TP is?
Half.
Half of RS.
Serious right now?
What?
Guess how long PW is?
Half.
Half of OR. So it's half the third side.
Yeah, we can't see it.
Yeah, we can't see.
Well, you can hear half the third side.
Yeah, but I'm not visual.
Yeah, I was showing you on the triangle. Do mid-segments have a point of concurrency? Do they all three meet in one place?
No.
No, they don't. They form a little triangle inside. Ooh, could I do the mid-segments of these guys now?
Yeah.
And make a little triangle in there?
That's right.
And then could I do the mid-segments here? And make little triangles there? And then could I do mid-segments here?
Indeed.
You can do that on infinitely, and it forms a fractal called the Sierpinski triangle.
Pinsky?
And it does some really amazing stuff. But sadly, we have to take a quiz, so we don't have time to go over the amazing stuff it does. So, instead, so on the quiz, it's only going to be day 1 and day 2.
Wait, you wrote it in blue too?
So you need to clear your desk. You may use a calculator. Kick people off the island.